All right, we're going to keep looking at some work problems. These ones are going to be where you are pulling something up or over a higher position. So a 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? So as you are pulling this right away, the cable is going, you're pulling up 200 pounds. But as that cable starts piling up on the top, it weighs less and less because you have less cable to pull. So there's less force pushing down on that from gravity, and it weighs less. So this is a variable force. So that means we're going to need an integral. So again, when we integrate these work problems, we're trying to integrate from A to B of our force function here, dx. Since this is a variable one, and they don't give us that equation of that variable work, or variable force function, we're going to have to come up with it. So what we're going to do here is imagine a little chunk of this somewhere along this rope, and we're going to use that to try to figure out how we're going to get that force function over there. So we're going to take that little amount here, our change in x, and that's going to become our dx here eventually. What do we got to do to move that? So that little amount right there is part of that 100-foot long cable. So let's try to figure out, what does that little amount weigh? So that little change in x there should weigh 200 pounds. That's the amount of force the weight or the amount of force of this rope, divided by the length of it, 100 feet. And if we divide that, we know that chunk, however big it is 2 pounds per foot. So each little chunk there weighs 2 pounds per foot. So now if we were to multiply that by however far away that chunk is, let's call it x feet, then that should be the amount of force for that little representative chunk of rope. So that would become then our force here is that, our force function here is going to become 2 pounds per foot times x number of feet, and that should leave us with a force of pounds, because if we have 2 pounds per foot times x feet, our units here of feet cancel out, and we're just left with 2x, and that would be in pounds, which is in imperial units, that is a measurement of force. So our force function here is going to be 2x, and that however far we move that. So now if we move however many chunks from the bottom here to the top, that should give us our overall work being done. So when we're doing this, the top one's at 0, the bottom one's at 100, so that would be our limits over here. So our limits are from 0 to 100. Each chunk is 2 pounds per foot times the number of feet, and then we're integrating that chunk dx. So if we integrate this now, that would tell us how much work is needed to pull that rope up. Antiderivative here being just x squared from 100 to 0. 100 squared is going to be 10,000 minus 0, or just 10,000 pounds, and we moved it feet, so this would be in, other way around, foot pounds of work. So that's how the amount of work needed to pull that rope up. Let's try some more of these pulling problem examples. All right, so next one says a leaky 5-kilogram bucket is lifted from the ground to a height of 20 meters at a constant speed with a rope that weighs 0.5 kilograms per meter. Initially, the bucket contains 40 kilograms of water, but the water leaks at a constant rate and finishes draining just as the bucket reaches the top. How much work is done to pull this? Okay, so here we got a new type of problem because we got some different things we're pulling. Last time it was just a rope. Now we got a rope that we're pulling. It's also attached to a bucket that has water. So in this one, when we're doing this problem, if we're going to find this work here, our work is going to be the amount that the bucket has, the amount of work to pull the rope, because there's a rope like our last problem, and we also got water that we got to keep track of. So we got to find what's the amount of work for all three of these things. Let's start with the bucket, because the bucket's probably the easiest of these three things to find. Move this over a little bit here. All right, so the bucket, as we're pulling this, never changes. The weight of that bucket should remain constant. So the bucket itself, there's no change to the bucket. The water's changing because it's leaking out, and the rope's changing because there's less of it as we pull, but the bucket never changes. So that 5 kilogram bucket, to find that, is a constant force. So this one, when we do our bucket here, should just be the force of the bucket times the distance that we're pulling it. So the force being applied to that bucket is the mass times the acceleration of the bucket times the distance we're pulling it. So here our bucket weighs 5 kilograms. And that's our metric units that we want. The acceleration due to gravity is known to be 9.8. And I know they didn't give it to us in this problem, but that would be given to you on the test, so don't worry if you haven't been in physics before. And then the distance that we're pulling it would be, looks like 20 meters here is the total. So 20 is our distance. So that one is a constant one. There's no change as we pull. If we multiply those together, it looks like we get 980 would be the amount of work for the bucket. Okay, so now let's go on to the next one here. Let's use a different color here. So next, let's work on the rope. All right, so our rope is kind of like the last problem. We want to figure out a representative little chunk here, our change in x, or eventually that's our dx here. So what is that representative rope if we have to pull it x feet up? Well, they give us that each chunk of the rope is 0.5 kilograms per meter. So if we take the 0.5 kilograms per meter times the number of meters, that should then be, that would be in kilograms, but kilograms isn't a force. We need that in, we need that multiplied by the acceleration due to gravity. So in this case, we need to take that times our 9.8. And that would give us the amount of force on this one. And this one is a variable force because as we pull that rope, there's less and less and less of it. So we do need an integral for this one. So we're going to do an integral from the start, which would be 0, down to where this bucket is, which looks like it's at 20. So 0 to 20 of our force function, and we know our force is going to be all this stuff. So there's all our stuff for our force here, and then times dx. All right, so now if we integrate that, that should give us the force, amount of force to pull the rope, or sorry, amount of work to pull the rope up. To integrate this one, we do have some constants here we could take out. 9.8 and 0.5 are both constants, so you could take that out as half of that is 4.9, sorry, 4.9. 0 to 8 of or 0 to 20 of just x now. Our antiderivative there would be 1/2 x squared from 20 to 0. So if you take 20 squared, that's 400. Half of that's 200. 200 times 4.9 is also ends up actually being 980. So the same amount of work, it takes the same amount of work to pull that rope as it does the bucket with what that weighs. All right, we got one last part now to this one. We got the water. All right, so how do we find the water here? The water leaks out at a constant rate. So initially, the amount of weight that the water is going to be is 40 kilograms. But by the time we reach the top, it's 0 kilograms. So let's set up to find the amount, kind of like we did with the rope, of how that's changing over time here. So initially, let's use it as maybe like some ordered pairs here. Initially, the bucket is going to weigh 40 kilograms, and the distance it is away is, the distance the water is away is 20. So this is at the start. At the end, what do we know about the bucket? Its weight's going to be 0, or it's, the weight of that would be 0, the mass of it. And the distance it would be is also 0. So what we can do now is figure out how that is leaking. The weight of it is changing over time. So if we just do like our little slope formula here, change in y over change in x, that'll give us that this is 40 over 20, or 2, and the top measurements in kilograms per the bottom measurements in meter. That's the same thing we were working in before, where it's kilograms per meter. So now if we pull that, our amount up, that should give us the amount of work needed to pull the water. So let's set up our last integral here. So we have an integral that we're going to again be doing from 0 to 20. And then we want how much this is going to weigh. Now this one changes over time here. So this, at the beginning, it was 20 kilograms, or sorry, 40, was it 40 kilograms? 40 kilograms of water. So at the start, we got 40 kilograms. So 40 kilograms, but that's not a force. So we need to multiply that by 9.8. So at the beginning, that's how much it's going to weigh, but it's decreasing as we go. So we want to subtract from that how much it's changing, which we know is our 2 kilogram here, minus our 2 kilogram, and that's not a force again, so we need to multiply it by 9.8. So now that would be the force acting upon that per meter times the number of meters. That would give us our force there. And now if we integrate that dx, then we have the amount of work needed to do that one. So what this turns into, if we do a little multiplying here, our integrals 0 to 20, this ends up being 392 minus 19.6 6x dx. So that's what we want to integrate. We can't pull out those constants unless you break it up into two integrals because we're subtracting there. So let's find our antiderivative. Would be 392x minus, this is now squared, half of that would be our 9.8. And we're integrating that from 20 to 0. So if we put 20 in, minus what we get with 0, the 0 one's just 0. So putting that in, we should end up that that is 3,920 is the amount of joules there. So now if we add those up, that would give us our total amount of work here done to move all of those. So our total work here for all three, add those up, 980 plus 3,920, and we get 5,880 joules of total work here. So that is how you would handle a problem like that. So when things are changing, you got to use integrals to solve. All right, let's have you try one of these ones. So this one is pretty similar to the last one. Let's start first, try to pause the video here, see if you can find the amount of work for the bucket to start. We'll start off easy and we'll go to harder here. So see if you can find the amount of work for the bucket. All right, hopefully you had a chance to read through that and try it. The bucket is not going to change in this particular problem. It's going to weigh the same thing the whole time. So we can just do a constant one. Our force here is 5 pounds for the bucket. That already includes gravity, so don't multiply that by any type of gravity. It's just 5. And then the distance is 30, and so there should be 150 foot-pounds of work needed to pull the bucket. All right, now let's get a little bit harder here. Let's go to the rope next. So how much force is needed to move the rope? So think back to the previous problems we did. See if you can figure out that one. You're going to need an integral. All right, hopefully you had a chance again to try this one. When we're looking at the rope here, if we have some representative change in x here, we're going to have to pull that x up here, and we're going to have to pull all those from this distance to this distance, which is 0 to 30 here. The weight of one of those is a ½ pound per foot. So if we pull that ½ pound per foot for x feet, we get our force function as 1/2 x. And so integrate that, and hopefully you came up with 225 foot-pounds of work to move the rope up. All right, we got one last thing in this one, the water. So see if you can now set up an integral here to find the water amount. You will need a integral on this one, as this is another changing one. All right, let's see what you came up with for the water. This one was definitely the toughest out of the three things to find. If we do like last time, we know at the start here that the water is 30 feet away, and the weight of it is 10 pounds, as it is said in the problem here. What about at the end? Well, at the end, we know it's 0 feet away when it gets to the top by that pulley. What's the weight of the water at the end, though? And that was the challenge on this one. One way to do it, we know that it's going to have to move 30 feet, and they told you the rate at which we're pulling is 3 feet per second. So if you work with that, you could say that we have, I'm going to flip this around 30 feet. This means 30 feet per 1 second. So if we did 3 feet per, or sorry, I'm going to go the other way here. That also means that every 1 second we move it 3 feet, and we're moving this for 30 feet is what it said here. So it's going to take 30 divided by 3, or 10 seconds for this to get to the top. So how much did it lose in that 10 seconds? Well, now we can use this statement where it says it loses 1/4 of a pound per second to figure that out. So if we take that rate, 1 pound per 4 seconds here, and times it by our 10 seconds, then we can figure out the weight of it. So we would get that it loses 10/4 of a pound by the time you get up there. 10/4 is the same as 2.5 pounds. But you got to be careful. That's the amount it loses during that. So how much, what's the weight of that at the end? Well, if we subtract it from the 10 we started with, 10 minus 2.5 means we still have 7.5 pounds at the end. So that would be the ending weight. So to set up our integral now, we want the starting weight minus what it's losing as we go. So do a little, if we did a little like slope type thing on here, we got our change in y over our change in x. That gives us 2.5 over 30, and that is the same also as 1/12. So we're losing 1/12 of a pound per foot. So our integral then should be from 0 to 30 of our starting weight minus what we're losing per foot dx. And if you integrate that, antiderivative would be this. And if you plug in 30 for that, 0 is not really going to change anything. If you plug in 30, it comes out to be 262.5 foot pounds. And so the last thing now to answer this one would be to add up the rope, the bucket, and the water, and we get our total. And if you do that on this one, so you got our 150 plus 225 plus our 262.5. The total work here is going to be 637.5, and this one is in foot pounds. So that's our total